Hi everybody. I was originally just going to put this video in with the AM section of the TUX1 video where I'm working on the Sansui TUX1 just to explain a little bit about AM and how it works so that you'll have a better understanding of how this tuner works in kind of a special way. But then I thought that's definitely going to make the video too long. So I thought I'd just do a separate one here. I'll release this before I release the final video for the Sansui TUX1, and I hope you enjoy it. A lot of you are just getting into this. I'm getting that from a lot of the emails that I get. And so for some of you, this will be really interesting, and for others of you, this will either be review or not interesting at all because you already know it. But what I'm going to talk about in this video is AM modulation and some of the properties of it and what an AM radio is, what's going on in the background. We're just going to strictly stick with what AM modulation is. So without any further ado, here we go. Okay, the first thing we're going to start with is just explaining what we have for a test jig. And all we have is a 50 ohm dummy load. This is just a 50 ohm resistor that we're going to put our signal across and that we can read with our test equipment across that. We'll get a little more into what this is later on in the video. For a signal, we just have a 1 megahertz sine wave at about 500 millivolts amplitude. That's it. It's simply a 1 megahertz sine wave. And if we look on our scope, it looks like this. So you've seen this many times. Now this 1 megahertz signal we refer to as the carrier signal. So all it is just a standing 1 megahertz signal. And if I were to connect an antenna to these two wires right here, I would actually be transmitting a carrier wave in the AM broadcast range. Now why is that? Because AM radio uses carrier signals from about 550 kilohertz up to about 1600 kilohertz or 1.6 megahertz. So 1 megahertz is kind of right in the middle of that band. So this is actually an AM radio signal that we're creating. Now, of course, we don't have an antenna connected, and even if we did, it's such a small signal it wouldn't carry very far. So we have a carrier signal, and that's all there is to it. Now, carrier signals don't really do us much good because you can't hear anything. You have to do something with that carrier signal in order to get your voice or your music or whatever it is you're trying to broadcast to come through the radio. Now, the practice of changing this signal or putting your voice or your music onto that carrier signal, we refer to as modulation. So when we modulate a carrier signal, we're actually putting our information on there that we want to be heard, whether it's a voice or music or whatever. So let's take a look at what that is. There's two ways that we modulate a carrier wave. One is through amplitude modulation, or AM for short. The other one is frequency modulation, or FM for short. Now we're not going to talk about FM a whole lot in this video because really that's not the point of it. But AM modulation is just what you may think. By taking this signal and varying the amplitude of it up and down, we can actually use this signal to carry that modulation. And it looks kind of like this. If I put a 1 kilohertz tone on the signal, it's going to distort this. Watch what happens. You see it becomes very unstable and jumps up and down. It's because the scope can't focus on that changing amplitude. So you just see it go up and down, up and down. However, if I turn it off, let's scrunch this signal way down together. Kind of like that. And if we turn our modulation back on, go a little more, we can actually see what's happening now. We can see the peaks and valleys of that modulation, and if we measured that frequency, we would find out that it's about 1 kilohertz, because I have a 1 kilohertz amplitude modulation being applied to that 1 megahertz carrier wave. So if you look here, it's trying to lock in on these peaks and valleys up here, but it can't because, again, it's a changing signal. So this is what it looks like when you have an AM modulated signal. And we have the top part and the bottom part, and we call those our sidebands. Now, if you notice, both sides of this signal are equal and opposite. So if you look at this little marker tag, this is 0 volts. So if you look here, that's a positive going voltage, and if you look down here, that's a negative going voltage. And if you add those two together, if you notice, there's always the same amount of voltage, negative and positive, at any given time during this signal. And what that means is that these two signals will mathematically cancel one another out, because if you have a positive voltage and an equal and opposite negative voltage, that positive voltage and negative voltage added together will equal 0. So if we tried to tune into just this signal as it stands right now, you really wouldn't hear very much. So I'm going to take if you notice, I have another channel turned on my scope, and I have the blue probe over here plugged into it, and it's not hooked up to anything right now. But we're going to do something. I have just a simple little germanium diode connected to our signal, and I'm connecting the cathode of that diode to my other channel of my scope. And we're going to just see what that does. And you can see what we're getting here is a perfect sine wave. Now, of course, it's jumping around because there's a lot of noise on my wires and everything, so the scope's having a hard time tracking it. But what you're seeing here is the demodulated signal, or just the modulation by itself without the carrier wave. Do you notice something strange about it? Something unique? If you notice, here is my 0 volt tag right here for channel 2. Do you notice the entire signal is riding above that voltage, that 0 volt? Okay? Whereas on this one, it's both sides. All that diode has done is it's stripped off the whole bottom or negative going peak of that signal. And all that's left is our 1 kilohertz tone. So I just made a very, very basic radio, because that's really what a radio does. The first thing that radio has to do is it has to tune in that signal, in this case 1 megahertz. Then it has to remove the 1 megahertz carrier wave to leave only the sound behind. And we did that with one component. Now, this is how a crystal radio works. By using a tunable coil to tune into the frequency you want to listen to, and then placing a diode on it to remove that carrier wave and to remove one of the side bands or one of the half cycles, we're left with the sound. If we were to connect our little earphone to that, it would be very weak, but we could hear it. And that's exactly how a radio works. Now, what would happen if I took that same diode and just flipped it around? What if I took the diode and I flipped the anode and cathode ends around? Let's try that. Okay, I now have a second diode added to this, and if you notice, the band is facing the signal instead of it's facing towards the signal instead of away. So this diode is in opposite polarity from this one. So all I'm going to do is we're going to go over to the scope and we're going to move our probe from here to here and see what it does. Okay, we're now on the scope, and I'm going to move this probe from the positive facing diode to the negative facing diode. And what happened? Now we're cutting off the top half and leaving the bottom half. And you can see now, with respect to ground, or to 0 volts, it's now going negative. So what we've just done is we've looked at our two sidebands. And that's what sidebands are. You have to remove one of them in order to leave the signal that you want to listen to of your modulation. Now, most radios, and why are we doing all this? Well, most radios will just have a diode, whether it's a vacuum tube diode or crystal diode, whatever, and we call that the detector diode. That's what it's called, the detector circuit. And this is just in very simple AM radios, and we're not talking about IF and all those other things. That's too much for this video. But that's really what the detector diode or the detector circuit does. And usually most radios will only have one detector in one polarity, whether it's the negative going or the positive going. They only have one. And the Sansui that we're working on, that TUX1, one of the things it's able to do is it's able to look at either one. And it is able to use both of them, so it splits them into two separate signals, a positive and a negative going, like this. And then it can actually take the difference between them and create an error. And essentially, we can use this side or this side. So let's say you have another radio station that's very, very close frequency to this one that's at 1 megahertz. And let's say it's kind of overlapping it, but let's say it's on this side of the band or this side, a little bit above or a little bit below. By doing this, that TUX1 can actually kind of shift a little bit away from that noise and reduce the noise to the station. So it's a really cool feature the way it does it. Now there's a lot more to it the way that circuit works, but essentially what they're looking at is the upper and lower sidebands. Upper and lower just means lower is the sideband that is on, this part that is a little bit lower than our carrier frequency, and this is a little higher, or upper sideband is a little higher than our carrier frequency. So that's essentially what it is. So I just thought I'd do that little short video here on what sidebands are and how a detector and a carrier wave and all those things are, how that works. And I hope that helps out a little bit. And when we start working back on the TUX1, I'll be talking about things like that, and maybe it'll make a little more sense what we're adjusting and what we're doing when we're calibrating it. Thank you very much, and stay tuned for the rest of the video.